The service panels in a multimeter installation can indeed be considered subpanels, and this determination has significant implications for how the neutral and grounding conductors are handled. The core principle is that when the service disconnecting means the main point at which power can be shut off to the entire service is located upstream of the panels, typically in the meter hub, the downstream panels are treated electrically as subpanels. This arrangement necessitates a separation of the neutral and grounding conductors within these panels, along with the removal of the bonding jumper. This requirement stems from the National Electrical Code, specifically Section 250.30, which addresses the location of system grounding connections. According to Section 250.30a, the service grounding electrode conductor must be connected to the grounded conductor at the service disconnecting means. This means that the connection to ground, including the connection to the water main and ground rods, must occur at the location of the service disconnect. Service disconnecting means must be the first point of disconnection or overcurrent protection on a line side of the service overcurrent protective device. There is an exception for separately derived systems supplied by a transformer, where the service grounding electrode conductor is connected to the grounded conductor at or ahead of the system disconnecting means or overcurrent device. However, in the typical multimeter installation described, this exception does not usually apply. Section 250.30b further clarifies that for systems other than service systems, the system grounding connections must be made at the source of the separately derived system. In the scenario where the service disconnect is in the meter hub, the panels downstream are not considered service systems but rather parts of a separately derived system originating from the service disconnect. The rationale behind this setup is to prevent parallel paths for neutral current. When the neutral and ground are bonded at multiple points, such as at the service disconnect and again at each downstream panel, the neutral current can split and flow through both the neutral conductor and the grounding conductor. This is undesirable for several reasons. Firstly, it can cause the grounding conductor to carry current, which is not its intended purpose. The grounding conductor is meant to provide a low impedance path for fault current to return to the source, facilitating the rapid operation of current protective devices such as circuit breakers or fuses. Secondly, the flow of neutral current through the grounding conductor can introduce noise and interference into sensitive electronic equipment connected to the system. Thirdly, it can create a shock hazard, as any contact with the grounding conductor could potentially expose someone to neutral current. By separating the neutral and grounding conductors at the subpoles and removing the bonding jumper, ensure that the neutral current is confined to the neutral conductor, and the grounding conductor serves only as a safety path for fault current. The equipment grounding conductor from the water main and ground rods are crucial components of the grounding system. The water main, if metallic and meeting certain criteria, serves as an effective grounding electrode due to its extensive contact with the earth. Ground rods, typically driven into the ground near the service entrance, provide an additional grounding electrode. These electrodes are connected to the grounded conductor at the service disconnect, creating a low impedance path to ground. This low impedance path is essential for clearing faults quickly and safely. When a fault occurs, such as a live conductor coming into contact with a metal enclosure, the fault current flows through the grounding conductor back to the source. The low impedance of the grounding path allows a large amount of current to flow, causing the overcurrent protective device to trip and to energize the circuit. Without an effective grounding system, the fault current may not be sufficient to trip the overcurrent protective device, leaving the metal enclosure energized and posing a shock hazard. The installation of ground rods must comply with NEC requirements, including the number of rods, their spacing, and their depth in the ground. Typically, 2 ground rods are required, spaced at least 6 feet apart and driven to a depth of at least 8 feet. The grounding electrode conductor, which connects the ground rods and water main to the service disconnect, must also be sized appropriately according to the NEC. The size of the grounding electrode conductor is based on the size of the service entrance conductors. It is important to note that the water main connection must be made within 5 feet of the point where the water pipe enters the building. This requirement is intended to ensure that the grounding connection is effective, as the water pipe may be interrupted by non-conductive couplings or sections further inside the building. In summary, when the service disconnect is located in the meter hub, the downstream panels are considered subpanels, requiring the separation of neutral and grounding conductors and the removal of the bonding jumper. This configuration is necessary to prevent parallel paths for neutral current and ensure the safety and proper functioning of the electrical system. The grounding system, including the water main and ground rods, plays a critical role in providing a low impedance path for fault current, protecting against electrical shock hazards. Understanding these requirements is essential for ensuring compliance with the NEC and maintaining a safe electrical installation. To reiterate, let's walk through the reasons why service panels are considered subpanels in this configuration and the implications. Firstly, the location of the service disconnect is the determining factor. If the service disconnect is located in the meter hub, it means that the power can be shut off to the entire service at that point. Anything downstream of that point, including the individual meter panels, is considered a subpanel. Secondly, the NEC mandates specific grounding and bonding requirements for service equipment. Section 250.24 typically requires the neutral conductor to be connected to the equipment grounding conductors at the service equipment. However, when the service disconnect is located upstream, this connection must only occur at the upstream location, not at each individual panel. Thirdly, the separation of neutral and ground is crucial for safety. Bonding the neutral and ground at multiple points creates parallel paths for neutral current. This can lead to current flowing on the equipment grounding conductors, which is not their intended purpose and can create a shock hazard. Fourthly, the bonding jumper, which is a conductor that connects the neutral and ground buses in a panel, must be removed in subpanels. This is because the neutral and ground are already bonded at the service disconnect, and adding another bond would create the parallel path issue. Fifthly, the grounding electrode system, which includes the water main and ground rods, must be connected to the neutral conductor at the service disconnect. This ensures that the entire system is properly grounded and that fault current has a low impedance path to return to the source. Sixthly, the equipment grounding conductors that run with the branch circuits must be connected to the ground bus in the subpanel. These conductors provide a path for fault current to return to the source from any equipment connected to the circuit. Seventhly, the metal enclosures of the subpanels must be bonded to the equipment grounding conductor. This ensures that any fault current that flows to the enclosure will be safely conducted back to the source. Eighthly, the size of the equipment grounding conductors must be appropriate for the size of the circuit. The NEC provides tables that specify the minimum size of the equipment grounding conductor based on the overcurrent protection device rating. Ninthly, the installation of the grounding electrode system must comply with NEC requirements. This includes the size and type of grounding electrodes, the size of the grounding electrode conductor, and the method of connection. Tenthly, it is important to properly label the subpanels to indicate that they are subpanels and that the neutral and ground are separated. This helps to prevent confusion and ensures that future electrical work is performed correctly. In conclusion, understanding the requirements for service panels that are treated as subpanels is essential for ensuring a safe and code-compliant electrical installation. By following the NEC guidelines and properly separating the neutral and ground conductors, you can prevent parallel paths for neutral current and protect against electrical shock hazards. Let's elaborate further on the practical implications and considerations when dealing with service panels configured as subpanels in a multi-meter setup. Consider the scenario where a multi-unit dwelling or commercial building has multiple tenants, each with their own meter and associated panel. The utility company typically installs the main service equipment, including the meters and the service disconnect, often housed in a meter hub or similar enclosure. From the service disconnect, individual sets of conductors are run to each tenant's panel. In this configuration, each tenant's panel is effectively a subpanel, and the electrical installation must adhere to the subpanel wiring requirements outlined in the NEC. One of the key aspects to consider is the identification and labeling of the equipment. The service disconnect must be clearly labeled to indicate that it is the main disconnecting means for the entire service. Each subpanel must also be labeled to indicate that it is a subpanel and that the neutral and ground conductors are separated. This labeling is crucial for future maintenance and modifications to the electrical system, as it helps electricians quickly identify the correct wiring configuration. Another important consideration is the sizing of the conductors and overcurrent protection devices. The conductors running from a service disconnect to each subpanel must be sized appropriately to carry the expected load of that panel. The overcurrent protection devices, such as circuit breakers or fuses, must also be sized to protect the conductors and equipment connected to the panel. The NEC provides tables and guidelines for determining the appropriate conductor and overcurrent protection device sizes based on the load calculations. Furthermore, the installation of ground fault circuit interrupter (GFCI) protection is essential in certain areas such as bathrooms, kitchens, and outdoor locations. GFCI protection is designed to detect small imbalances in current between the hot and neutral conductors, which can indicate a ground fault. When a ground fault is detected, the GFCI trips the circuit, quickly de-energizing the circuit and preventing electrical shock. The NEC specifies the locations where GFCI protection is required, and it is important to comply with these requirements to ensure safety. Surge protection is another important consideration, particularly in areas prone to lightning strikes or power surges. Surge protective devices, SPDs, are designed to protect sensitive electronic equipment from voltage spikes that can damage or destroy them. SPD can be installed at the service entrance or at individual panels, and they should be selected based on the voltage and current requirements of the equipment being protected. In addition to the technical aspects, it is also important to consider the administrative and regulatory requirements. Electrical installations must comply with the local building codes and regulations, which may be more stringent than the NEC. It is essential to obtain the necessary permits and inspections before starting any electrical work and to ensure that the work is performed by a qualified and licensed electrician. Regular maintenance and inspections are also crucial for ensuring the continued safety and reliability of the electrical system. The panels and equipment should be inspected periodically for any signs of damage, wear, or corrosion. The overcurrent protection devices should be tested to ensure that they are functioning properly, and the grounding system should be checked to ensure that it is still effective. Any deficiencies should be addressed promptly to prevent potential hazards. In summary, when dealing with service panels configured as subpanels in a multimeter setup, it is important to consider the technical, administrative, and regulatory requirements. Proper identification and labeling, conductor and overcurrent protection device sizing, GFCI and surge protection, and regular maintenance and inspections are all essential for ensuring a safe and code-compliant electrical installation. Furthermore, it is always advisable to consult with a qualified and licensed electrician to ensure that the work is performed correctly and in accordance with all applicable codes and regulations. Let's discuss some common mistakes and troubleshooting tips related to service panels wired as subpanels. One common mistake is failing to properly separate the neutral and ground conductors in the subpanel. This can occur if the bonding jumper is not removed or if the neutral and ground buses are inadvertently connected. As mentioned earlier, this creates parallel paths for neutral current and can lead to various problems. To troubleshoot this issue, visually inspect the subpanel to ensure that the bonding jumper is removed and that the neutral and ground buses are completely isolated from each other. Use a multimeter to verify that there is no continuity between the neutral and ground buses. Another common mistake is improperly sizing the conductors or overcurrent protection devices. Undersized conductors can overheat and potentially cause a fire, while oversized overcurrent protection devices may not provide adequate protection against short circuits or overloads. To troubleshoot this issue, refer to the NEC tables and guidelines to determine the appropriate conductor and overcurrent protection device sizes based on the load calculations. Verify that the conductors and overcurrent protection devices in the subpanel are correctly sized. Another potential issue is a loose or corroded connection. Loose connections can cause arcing, which can generate heat and potentially start a fire. Corroded connections can increase resistance and reduce the effectiveness of the grounding system. To troubleshoot this issue, visually inspect all connections in the subpanel for signs of looseness or corrosion. Tighten any loose connections and clean any corroded connections. Apply an anti-corrosion compound to the connections to prevent future corrosion. A ground fault can also cause problems in a subpanel. A ground fault occurs when a live conductor comes into contact with a grounded surface, such as a metal enclosure. This can create a shock hazard and potentially damage equipment. To troubleshoot a ground fault, use a multimeter to check for continuity between the hot and ground conductors. If there is continuity, disconnect the circuits one at a time until the continuity disappears. This will help you isolate the circuit with the ground fault. Once you have identified the faulty circuit, inspect the wiring and equipment connected to that circuit to find the source of the ground fault. Another troubleshooting tip is to check the voltage at the subpanel. Use a voltmeter to measure the voltage between the hot and neutral conductors, the hot and ground conductors, and the neutral and ground conductors. The voltage between the hot and neutral conductors should be close to the nominal voltage, such as 120 volts or 240 volts. The voltage between the hot and ground conductors should also be close to the nominal voltage. The voltage between the neutral and ground conductors should be very low, typically less than 1 volt. If the voltage readings are significantly different from these values, it may indicate a problem with the wiring or equipment. Finally, it is important to keep accurate records of all electrical work performed in the subpanel. This includes the date of the work, the description of the work performed, the materials used, and the name of the electrician who performed the work. These records can be helpful for future troubleshooting and maintenance. In conclusion, troubleshooting service panels wired as subpanels requires a systematic approach and a thorough understanding of electrical principles. By following these tips and being aware of common mistakes, you can effectively diagnose and resolve many issues. However, it is always advisable to consult with a qualified and licensed electrician for complex or potentially dangerous electrical problems.